So let's see a weak acid strong base titration now. So we have ethanoic acid, which is a weak acid, and sodium hydroxide, which is a strong base. So that's the salt, sodium ethanoate, and water which is produced. Now the acid and the base react 1:1 ratio. Now the concentration of the ethanoic acid is given, and you have 50 centimeter cube of this, which means that this is found in the flask and that the NaOH is added from the burette, which means that when you're finding the pH, the initial pH will be the pH of the ethanoic acid. So you're more likely to end up with a graph that starts at a low pH. Now, let's calculate the pH at each point. So at the beginning, we don't have any NaOH, so we have just the ethanoic acid. So you will need to find the pH of the ethanoic acid. So for this, you're given the Ka value, so you can get that from the data booklet. So from the Ka value, you can get the H plus concentration using the expression here. And the pH, if you calculate it, you should get a pH of 2.37. So the graph should start at 2.37. Now, once half of the weak acid has been neutralized by the base and converted to the salt, in the mixture, you're going to have a mixture of the weak acid and its salt. Now, whenever you have a weak acid and its salt, this is called an acid buffer. And this area of the graph will be very resistant to pH. A buffer actually resists small changes in pH. So the graph will be relatively stable. It's not going to change. The pH will not change by a lot. And at this point, when exactly half of the acid has been reacted, the amount of acid and the amount of salt, the concentration of acid and the concentration of salt in the mixture is exactly the same. So because they are the same, in that expression here, we can see that A minus, concentration of the salt, and concentration of the acid will be the same, so they will cancel out. So at this point, Ka will be equal to the concentration of H plus. Therefore, pKa will be equal to the pH. Which means that at half equivalence point from the graph, we are able to find the pKa value of the weak acid based on the pH value. But this is only valid when you have a weak acid reacting to a strong base. Okay, now let's move on and say that we have added more of the NaOH. So we are 1 centimeter cube yet to reach the equivalence point. Now, if you have 50 centimeter cube of this and you have 49 centimeter cube of this, and because they are of the same molarity, which means that you will have 49 centimeter cube of the salt that is going to be produced and 1 centimeter cube of unreacted acid. So this is going to react, it's going to produce this. So you have the salt and you have the acid. So you have 1 centimeter cube of 1 molar ethanoic acid, and this is present in 99 centimeter cube because the total volume here is 49 plus 50. So have 99 centimeter cube of solution in the flask. Now from this, I can find the concentration of CH3. So number of moles of ethanoic acid. So number of moles is concentration times volume, and this number of moles is present in 99 centimeter cube. So the concentration, the new concentration of the ethanoic acid is number of moles divided by volume. So that's the concentration of the ethanoic acid. Now the concentration of the salt, so the number of moles of salt will be the same as the number of moles of NaOH used, because it's the NaOH that is converting the ethanoic acid to the salt. So the NaOH and the salt will have the same number of moles. So to find the number of moles of NaOH, number of moles is concentration times volume. So concentration of NaOH times volume of NaOH used is 49. So that will give you the number of moles of the salt. Now this salt is present, this number of moles is present in the total volume of 99 centimeter cube. So from the number of moles and the volume, we can get the concentration of the salt. So concentration is number of moles divided by the volume times 1000. That's because it's in centimeter cube. So that's the concentration of the salt. So the salt and the acid have different concentrations, because remember that a weak acid is not going to give the same amount of H+. So you don't have the same amount of H+. The amount of H+ is actually not known here. So the amount of salt and the amount of H+ is not the same, because it's actually a weak acid. Now, based on the expression, so we know the value of Ka. So from the pKa, you can get the Ka. And then the concentration of the COOH or the salt has been found. The concentration of the weak acid has been found. So from this, you can get the concentration of H+. And from the concentration of H+, you can get the pH value. Now the Ka value, this is given from the question here. So the Ka is given. So you can apply the Ka here and then find the value of the H+. And here as well, from the Ka value, you can get the pH at half equivalence point. So here, if you do the calculation, so here the pH at half equivalence point will be 4.74. So at this point here, the pH is 6.44. So at this point here, when 49 centimeter cube of the base has been added, we have actually moved out of the buffer range here. So here, if you look at the graph, so you have the equivalence point over here. So this is 50 centimeter cube. So at half the equivalence point, at 25 centimeter cube, here the pH is equal to the pK. And over here, you see the buffered region. So the buffered region is where the concentration of the acid is equal to the concentration of the salt. So that at this point, Ka is equal to H+ concentration. So if you look at the graph, you can see that the initial pH is fairly high because it's a weak acid. And the pH will stay relatively constant until the equivalence point. So this is the buffer region. And there's going to be a jump in the pH at equivalence point, which is not as much as the jump when you have the strong acid, strong base titration. And then after the equivalence point, the curve is going to flatten. And then after pH 7, we're going to have more OH minus in solution. And here you're going to have the part that is the same as for a strong base pH.